Welcome to this interview here on location at the beautiful home of Ray Tomes from the Cycles Research Institute. And Ray, we're going to be talking about geological cycles.
Yep.
What can you tell us about that, Ray?
I first became aware of geological cycles when I found this book in the Auckland University Library. It's called Megacycles.
Yes.
And mega they are.
Who wrote that, Ray?
It's the proceedings of a geological conference.
Yep.
And it's edited by George Williams, who's an Australian geologist.
Yes.
And he's done some other interesting work which we might talk about some other time. He starts off by saying it covers a wide range of things about geological cycles, but the first interesting thing is he mentions that there are a series of geological cycles that they generally accepted were there. The longest one was 600 million years, then there was a 300 million year, 150 million year, and then one about 74 million years and 37 million years. And
am I hearing some halves in this,
Right?
Ray?
You're hearing some halves. So I mentioned that in climate as well, because those things show up in climate, and quite clearly climate and geology are intimately related, because when you get more rainfall, you get more stuff washed down and you get more deposits, and it changes the nature of the geological deposits. So they're connected, and as temperature and other things change,
I see.
The things are in there. So it was clear to them that there was this doubling. We've seen that in a lot of other places. Quite likely they were not aware of the work of Edward Dewey, where he found a whole lot of economic cycles and cycles and other things in more human scale. For example, he had cycles of 1.11, 2.22, 4.44, 8.88 years, 17.75, 35.5, 71 years. All these things have been found that match those. But he also found ratios of 3 from some of them and other ratios, but mainly 2 and 3. So this is another case of that, and we've got lots of other cases. More recently, independently of these things, astronomers found some short period cycles in the Sun, 154 days and 77 days, and there's some other ones, and I found those are in some short-term weather records as well. But you have to look for them to find them.
Okay.
So we've got these long cycles. Williams mentions that they maybe have astronomical significance because they did find some connections to that, and they reckon that the Magellanic Clouds would orbit our galaxy in 1200 million years.
Magellanic Clouds, right?
Yeah, they're the two little galaxies. Mm-hmm. You can see them in the southern hemisphere. You can see them in the night sky, not too far from the Milky Way.
Yes.
And he got some information that they should orbit the Milky Way galaxy in about 1200 million years, so double the longest cycle they've got. So he thinks there's some. They were leading towards some cosmic connection between these cycles and what's happening on Earth, because it's very hard to explain where does a 300 million or a 600 million year cycle come from. When I talked about to displace something like a swing and it swings back again in displacement, it's hard to imagine what it is that's taking a few hundred million years to come back to where it was. What's the force and what's the there? So it does seem that you're looking at some sort of cosmological things to explain that. When I first developed harmonics theory, and I began to look for some of these long cycles, and I researched all these different ones to see whether the patterns were there. Because it does expect these ratios of 2 and also 3 and other numbers occasionally. I came across an article that a group of American and Australian astronomers had worked together to look in 2 opposite directions in the sky, and usually they do big areas of the sky. This one they called it a pencil beam. They're just a little skinny beam, but very thoroughly out to a great distance. They got the galaxies and how far away they are. And so they did this in 2 directions so they could see where we were in the whole thing. And what they found was, they were quite surprised. They described them as megawalls of galaxies. Interesting, isn't it? Megacycles and megawalls of galaxies, of galactic clusters. So the distances are not the distance between galaxies, a distance between superclusters of galaxies, very massive ones. And the distances, they use very strange units in cosmology, because it depends on the Hubble constant, which is interpreted as the rate of expansion of the universe, which we'll argue about another time. They don't know what that is exactly. They didn't have it pinned down. At the time that some of this work was done, they were debating whether it was this figure or another figure that was twice as big. So everything was done in terms of these units, which have the inverse of the Hubble constant built into them. And they're done in terms of velocity units, which I don't believe is velocity as well. So the units are very strange. And what they really mean is there's a red shift. There's a variation red shift. But what it came down to is, in terms of their interpreted velocity, that they get, there were these steps. And it was 128 of the inverse Hubble's constant steps, which actually translates to 12,800 kilometers per second, equivalent redshift. So that's actually a significant proportion of the speed of light, right? 4%. These steps are 4% of the speed of light steps, so you can't have too many of them before you get to the end of the universe that we can observe.
So they're looking to estimate the size of the universe.
Well, they're not doing that, but they're looking to. They weren't expecting this. And they got this, and it's a very regular pattern, but they don't know what the factor is to convert that into real units that we know. So at that time,
and the Hubble constant might get reevaluated yet again.
Now, at that time, I had made a prediction. I couldn't say which was the exact correct Hubble constant, but they were harmonically related values. So I had 4 possible values: around 48, 72, 64, and 96. Kilometers per second per megaparsec is the units they use. So, and which I revised slightly downwards later. And this one would work if this cycle present in the geological cycle, 500, which I haven't mentioned Afanasiev yet, have I? No, well, he came later. But from this, I was working out that the spacings between these galaxies probably did correspond to the 600 million year cycle that they're reporting there, in the way of it being a wave structure. If there's a giant wave oscillating in space, the distance between the nodes was 600 million.
And at every
years.
node is where you're likely to find a cluster.
The clusters of galaxies.
Yeah.
And so the oscillation, the time that light takes to travel that distance, is 586 million years. Which gives the geological cycle. The oscillation period is 586, and the distance is 586 million light years.
Because we're right in that wave.
And a number of times I've told this to physicists and astronomers, and they say, "Oh, you're doing numerology." I say, "No, I'm not doing numerology." We're doing numerology. You're equating light years with years. I say, and it's just because it's the same number, you think that's meaningful. I said, "No, I'm not doing that." I said, if you have a wave that's 586 million light years long, how long does it take to oscillate? Well, what's the equation for that? So we go through the equation. Oh yes, it's 586 million years. That's why light years, astronomers mostly use parsecs and bigger parsecs.
And that's what, 13.2 trillion light years?
1 parsec is about 3 1/4 light years.
Oh, okay.
Which means when you see 2 numbers, one in parsecs and the other one in years, you don't notice any connection between them. When you put them in light years and years, you immediately notice I've got the same thing twice. It is the same. It's a wave. And so what I propose is this standing wave structure. People have suggested this looks like some sort of wave phenomenon when they saw the galaxies like that, but they thought it was a wave phenomenon from the early universe. What I'm saying is it's a wave phenomenon that's still there because these geological cycles are still happening. Right? So it's an existing wave phenomenon, and that is part of the evidence, in fact, that the Big Bang is wrong. That it's not happening. We'll come back to them another time. So
we're not riding on the waves that are like, we're not looking back on an echo or something that was there.
No,
this is happening
that's right now. These waves are still waving, still oscillating. Now, the next thing in this step was that I made a trip to Russia to a Cycles conference, and it was a particularly interesting event because it was a centenary of Chizevsky, who's probably the most famous. They particularly wanted to have it for that because he's the most famous cycles researcher. There's other ones that have been good. Both Russia and America have had a big history, and some in Europe also of cycles research.
Yes.
But I think Chizevsky was probably the most multidisciplines person studying cycles that there's been, and Dewey would be close to him as well in that he's studied many things as well. Well, he created a foundation that could do the many things, so he could probably got an even bigger scope, but there's other people doing a lot of it as well. At that conference, I was surprised we got there. I thought I'd offered to give a talk, and when I arrived, I discovered that they decided I was the keynote speaker. So I gave a talk on harmonics theory.
Yes.
And they had over 500 people at this conference, so that was quite spectacular for a cycles conference. Let's hope we can achieve that sort of thing in the future again.
Yes, indeed.
So at the end of my talk, which I was speaking in English, and of course all Russians, they had a lady translating from English to Russian. The first guy came up to me and shook my hand and said, look, he said, I understand English very well and I understand Russian very well, and this lady gave the best translation of a scientific talk that I've ever heard. It was absolutely perfect.
How fortunate.
Yeah, so that was really good.
Yep.
And then another Russian came up to me, and he didn't speak any English, but he'd understood the talk because the lady did a good job of translating.
Wow.
And he thrust this book into my hand.
Yes.
It's what that says in Russian, translated to English, says Nanocycles Method, and it's Professor Afanasiev.
May I hold that up for
Yeah,
a moment?
it's Professor Afanasiev, who's the professor of geology at Moscow University.
Yes.
And what he devised is a method of measuring the age of geological deposits more accurately than any of the methods that are generally used. Now, this method is not known in the West. The discovery of it happened probably to a large extent because of these amazing salt mines they've got. They've got these salt deposits that go back millions of years, layer and layer of salt, and by measuring them, it's similar to the varves you get in rock deposits that have been laid down by silt coming down in rivers, and each year there's a different amount of rainfall, so you get a different amount of silt, and you get the thinner and the thicker particles and all that layout. And the same thing that we've seen in the layers of ice in the Antarctic and Greenland and so on that are put down. So these things give us long-term measurements of climate in the deposits. Now they can find them in the rocks as well, but they did a lot of their work on these ones, and what they found is, and this has been reported by other people as well, the moon, we have to talk about the moon for a moment. The moon's orbit is quite complicated. Let's say that the flat thing here is the Earth's orbit around the sun.
Okay.
Right. Now we know the Earth has got an axis tilted, so it's going around like that.
Yes.
And this axis precesses, but that's over 25,000 years, so we won't be worried about that longer period, initially anyway. And the thing is, the moon's orbit is more lined up with the plane of the Earth's rotation, but not quite. It's 5 degrees off. So this is 23 degrees tilt, and the moon's orbit is 5 degrees off that, and it wobbles around. So sometimes it's 18 degrees, sometimes it's 28 degrees tilt relative to the plane of the Earth's orbit.
Are those the Cycles of the moon?
No, that's a separate thing.
Okay.
But it's similar periods at some of those.
But that orbital plane is going back and forth.
It's not so much doing that as relative to the Earth's equator, it's precessing, and so that means that sometimes it's more than this and sometimes less. But when it's in between, it's tilted the other way. So that's going around like that. Plus the moon's elliptical orbit, and it's precessing going the opposite way to that. It's a very complicated arrangement. The important thing is that this business of the tilt goes through a cycle. That operation goes in 18.6 years. And what Afanasiev says, there's a number of cases of 18.6 year cycles reported in things, and there's a number of cases of 9.3 cycle, because it doesn't matter which node you're at, it has the same effect, whether it's ascending or descending one. So this is all based on the measurements of that lunar cycle being present in these deposits, originally of salt, but it's also applied to the varves in rocks. And so we get. It's not always been It's not always been that same period, 9.3 years, because the moon is gradually getting further away from the Earth. That means that its orbit changes and the rate of precession of that orbit changes. So over a long period of time, it's quite substantial. So if we
have we been able to measure earlier times? With different cycles?
So he's done that, and what he shows is he's got this big table which I'll hold up here, and you can see Right now, it's 9.298 years.
Yes.
Actually, 9.3. If you go back 0.2 million, just 9.296, and you go back 0.4 million to 9.237. And he's got this table running all the way out to 600 million years, right? But that's not the end of it. If you've got a 9.3 year cycle, after one cycle, the peak of it occurs 0.3 of the way through the year. And after 2, 0.6, and after 3, 0.9, so it's nearly back to the same place on the year.
Yeah.
And it turns out that after 3 cycles, then 3 cycles, and then 4 cycles the next time, it will come back to the same place. And that cycle averages 9.3 divided by 0.3, which is 31 years. And he's got that as a second entry here, 31 years. So when you see these deposits, you can see the 9-year cycle, but you can also find a 31-year cycle there, because the seasons, it's important when that happens, because there may be a rainy season, say, and it's important when it happens in the seasons.
Yes.
And he even gives a third and a fourth one there, and I don't know how often they find those. But this table goes on and gives all these values.
Yeah.
So now you find a deposit, and these are all calculated from the changes in the moon's orbit going back this vast amount of time. And they have the moon's orbit with huge numbers of decimal places on all of the parameters, right?
Yes.
Worked out going all the way back there as the moon gradually gets further away. So they now find a deposit some time back, and there'll be a cycle in it, and there'll be the second cycle, this one that relates to fitting in with the seasons, and you look those up in here and you run down the table and you say, that's just teensy bit less than that one at 10.8. All right, it's about 10.78 million years, and you can date the deposit from that. And so it's a method of accurately dating deposits all around the world.
Yeah, and we're finding differences as a result of the changes in the orbital path of the moon from galaxies far away, and and cycles of long time ago. Oh, the clouds far away.
Oh yeah. So with this method, it's interesting. He connects with George Williams because he gives 580. He gives this longest cycle as 586.24 million years.
Yeah.
That was given us by these guys as 600 million, around about.
That's close.
And so it's close enough. And we knew that there was the slightly lower figures on the shorter cycle, so we would have expected to be about 590ish. And he says 586.24. Now that figure, when I combined it with that, I could estimate what the correct Hubble Hubble constant would be.
Yeah. And
I got 71.2. Now, just recently, and I worked that out 2 decades ago,
yes,
the Hubble constant's got a lot more accurate since then, and the last 10 determinations that have been made, when I average them together, it gives 71.2.
71.2 on average.
Yes. So that says, with that value, it says that the spacings between those galactic superclusters are 586 million light years, right? It agrees perfectly with the geological one.
Wow.
Yeah. So we've got evidence of the standing waves, and we'll have another talk where we talk about evidence for other standing waves, and we'll bring this one together with 3 or 4 other ones that show there are standing waves at many scales in the universe, right from subatomic particles through to these supergalactic ones, and probably bigger. So that's the picture there. It's interesting that this method is not known in the West. I tried to put it into Wikipedia, and the result was certain geologists come along and said, look, there's these methods of dating deposits. There's radio dating, there's this, this doesn't exist. I said, well, it's not known about in the West, but it's well known in Russia. And a number of different people have researched on this, and they've done this. I'm trying to provide this information. No, deleted it. And you can fight a battle for all you like, but stuff gets deleted. Now, interestingly, I wrote a paper on that on Put in Cycles Research Institute website about the 2 things, the spacing of the supergalactic clusters and this geological cycle, and how it's evident for a wave.
So people will be able to link across or see the references or see the writings that you did on cyclesresearchinstitute.org.
That's right.
If they want to know more about what's been discovered.
But the interesting thing is today, when I was looking up, trying to see whether Professor Afanasiev had a website, it's a moderately common name, it seems. There's a number of Afanasievs, but he's not actually there. There is a geologist, he may be a son or something, I don't know. But the interesting thing was, I found a number of papers that people at universities have now published.
And as you find more, they'll be posted on the website.
They actually quoted my paper about the relationship between those two.
We'll link to that too.
So this is an idea which is starting to get accepted, and it helps that I could tell them what the Hubble constant was way before they managed to work it out themselves. Those things always help.
Yes.
I first gave a reasonably accurate figure in 1993. So now that's the longest geological cycle. But I put up a chart of the harmonics, which we can put on here, showing the calculation of how the harmonics goes out, and it makes these. There's a wave of the strongest ones, and it typically, whenever there's a very strong one, there's another one at a ratio of 2 above or below. We know about the 2s. Also at 12 or 24, but a very strong one occurs at a ratio of about 30-something thousand usually. But there's all these 12 and 24s ones in between, so you get this sort of effect coming.
And these are sort of universal harmonic
universal
observations.
Harmonics. Now, this is one of the things I saw when he passed me. Did I mention about him passing me this book? This is a graph.
Yep.
By Professor Afanasiev. It runs from a year to a billion years, and it shows
billion years.
Yep. So each of these, see, this is going 1, 2, 5, 10, 20, 50, 100, 200, 500, 1,000 years. 2, 5, 10, 20, 50, 100, 200, 500,000, a million. 2, 5, 10, 20, 50, 100 million. 200, 500 million, a billion, 2 billion. Oh, is that billions? It might be. But anyway, what you can see there, the number of occurrences each round of cycles, and there's a structure there. And when he saw my graph go up, he said, I presume he said, because we couldn't talk to each other in any common language, but I presume he said, this guy's got the theory that goes with what I've observed. And when he gave me this, I went, this guy's got the observations that go with my theory.
Extraordinary.
So this has been an interesting one for me. One of the things I want to do with this is, if I most of the book is a table. The writing is not that great, but not that much of it. But it's quite technical because it's about the moon's orbit and the calculation of these things. So it requires a person who's got some astronomical knowledge and some geological knowledge and some ability to translate. So I would like to get that translated. So maybe someone will see this.
Maybe they will.
And they will say, I could do that. And I would like to try and get that book translated into English because it needs to be. From Russian, yeah.
Very good.
So then we will have more information, but he does list a number of other specific cycles in there. One of the other things that came out from getting his more accurate figure, up until then, I had thought that the Hubble scale would be the time period associated with that would be the biggest scale, right, in the universe. And I was working on that assumption. And there was a funny little coincidence that happened, that as you calculate out the harmonics, you get lots of 2s and 3s and the occasional 5 and 7, and you get a long way down before you get an 11 and a 13. And if the Hubble scale was the number 1, we wouldn't have got to those yet by the sort of scale that we're used to the cycles in our lives of years and things. But there seemed to be a 13 ratio there between the cycles in the hundreds of years and the cycles in the thousands of years. So like the 2,300 year cycle I mentioned before, that one is 13 times one of the other shorter cycles that's well known. And so that was a little bit of a mystery, because that didn't seem to be right.
Some things double, sometimes multiply by 12, and this may be multiplying by 13.
But then I had the figure for the longest cycle, but I was out when I got his figure, I was out by by about 0.7%, and that's why my 72 changed to 71.2, right?
Oh my!
Or nearly 72.
Yeah.
And it turned out
Yeah.
it's because of that 13, and further up's an 11. Because 11 times 13 is 143, which is very similar to 12 times 12, which is 144.
Yes,
and that explains the difference. So the pattern I had, it turned out I was looking at the wrong part. The correct part, if you start from one up there, is the fundamental cycle of the universe. The part we were looking at was this part, not this part, right?
Okay.
And when I did an analysis to work out the longest cycle in the universe, it got an incredibly good fit for these cycles being the longest cycle is vastly bigger than anything that the Big Bang people imagine. Now,
and a lot of this started with looking at the physical evidence,
yeah,
the geological data.
yeah, but the
then you added harmonics theory to that.
When I got the fit to the cycles I'd put in to fit that long period,
Yep.
it came out with a couple of extra things that I hadn't expected. For example, one of the cycles that said should be very strong in the range of years was the 9.6 year cycle,
Yep.
which we know does exist in them things and does not fit Dewey's pattern and didn't fit the patterns I'd got up to that point either. But it did predict that one. So that was a confirmation that that very long cycle is correct. It's predicting new things that we didn't know why they were. Well, not new things that were happening. It was showing that should be the case, but we didn't know why it should be the case up till then. Dewey had these few rogue ones, cycle periods that didn't fit the other ones. Once I did this, there don't seem to be any of those anymore.
But there's a confluence, there's an interconnection, and those combine.
So we'll talk some more about that fitting the longer cycle.
Yes.
But the geological cycles, there's one more thing to come in there, which we'll look at a chart of the geological ages, and we'll find that the geological ages are multiples of 26 2/3 million years long. They're either that, 53, or 80. And you'll find one's 80 million years, another one's 53, another 53, and so on. Some time ago, there was a report that there was a cycle of 27 million years, and then another time they said 26 or 27 million years in mass extinctions. That's a separate topic, but we're going to do it now. Mass extinctions are again intimately tied
Which correlates as a half.
Yeah, they're intimately tied up with the geological record because when you get a mass extinction, there's one of these big breaks in the one of these big things in the geological record. Now that period that they gave for the mass extinctions, there's graphs showing, and we'll put one of those up, showing how many species or whatever got totally extinct over the last 600 million years again, and there's peaks and troughs in that. And the interesting thing is that there's a set of peaks that are about 27 million years apart, but there's a modulation on that. You get bigger peaks and smaller and bigger, and it turns out that you get bigger peaks where a 27 million year cycle and the 37 million year cycle come together. Remember, the 37 was the one you go from 586 and you halve down, you got to 37, so that was mentioned as a geological cycle. The two of those together, there were beats in the. You can see the beats of them in the record of the number of species going extinct.
It's remarkable that he could look at these layers in geological records and realize that there's more than one cycle influencing it, and actually pick them out.
These mass extinctions, it's worth mentioning what exactly happens. There was a big one at 65 million years ago, which was the dinosaurs went extinct. So most people have heard about that one. And people have talked about, was there a giant meteor or something like that? If you've got a regular cycle like that, you've got to have a source of regular giant meteors, which doesn't seem awfully likely.
No.
One thing proposed was that the sun, as we go around the galaxy, we don't do an orbit like the planets do around the Earth, around the sun, because the sun's got nearly all the mass of the solar system. We do elliptical orbits. We don't get elliptical orbits around the galaxy because there's so much matter in the plane of the galaxy that in actual fact, as it does a more or less ellipse, but it goes ducking up and down through the thing because of the attraction of the plane.
Yes.
And it was possible that we were travelling through the plane of the galaxy every that often.
So we're on a merry-go-round, just like a horse going up and down on a merry-go-round, crossing an orbital plane of the galaxy.
But the best estimate they've got of that is that it's 62 million years, which means we would cross through every 31, which is a bit off from the 26.7. Right. But when I go to the harmonics theory, when I take that 26.65 million year period, which is the best estimate I can get from all the data that's available, then I compare it to the 586.24 million year period. It goes into there 22.00 times. In other words, there's an 11 ratio there occurring from the 293 million down to that, an 11 ratio. And remember, I found a 13 ratio further down. And that was the expected arrangement, that you'll find the 11 at a higher level than the 13.
And it's not unprecedented for crossing through the mid-range to create a crisis.
We'd expect it to, because we're going to get a lot of dust in that. But it doesn't appear that that's the cause. More recently, someone has come out with a different set of data. They said originally we found the 27 million, or 26 million, and now we found 62. First of all, I thought they've just transposed the digit to 62 from 26. But no, they reckon it is 62. But I don't know I don't know why. The data was very clear that there was this other cycle before. I find it suspicious that they now have got this other figure. I don't know what's going on. I see other cases where this happens as well. I'm not sure. Sometimes people might find what they're looking for. I don't know. I'm not saying that's definitely the case. But to me, the data is very clear on the 27 million year one.
Indeed.
So that's the mass extinctions, and people ask me, when's the next one? And there's two answers to that.
Yes.
One of them is 27 million years after 65 million years ago, is 38, and then 11 million years ago, so the next one would be in 16 million years. If you take the 37 million year, it comes slightly different place, but we're not really expecting it for 11 million years. The other answer is, we appear to be in a mass extinction now, and that is probably due to human activity.
So it's not part of the cycle.
It's
our
not
own
innovation.
invention.
Yeah, right. Yeah. It wouldn't have been predictable from that past pattern. It's humans have had having a big enough effect on the Earth to be wiping out many species, and so that's. There's a lot of humans are making a lot of efforts to save some.
Yes.
We're going to go and visit territory in Matangi Island up the coast here, where a whole island has been cleared of all predators, so that the native New Zealand bird population, but many of which walk on the ground and don't fly, can be preserved. And the reason they didn't fly is before humans came to New Zealand, there were
no predators.
There were no significant predators. Well, the only predators were birds. The only mammal was a bat. So that was more as a bird itself. Yeah. And the only other one is a tuatara lizard, which is not a great big thing, and it's not fast enough to catch anything.
So there you are. So we would be going with the trend to have the species not continue to become extinct and life to flourish a little bit more if we change the way that we're intervening, because we're not in a cycle of mass extinction right now. So we really can make a difference and reverse some of what we're doing.
Yeah, because it's not a cosmic effect that's doing this. Maybe there is some cosmic effect. But what's suggested by this is that all of those cycles are cosmic cycles, the galaxy wave, and you can actually see within that one. I mentioned that these regular ones were at these spacings that they found in the supergalactic clusters, but in actual fact you can see the presence of a half and a quarter in that as well, just like there are in the geological cycle. You can see those other shorter ones there.
It's extraordinary that a library of our cyclic history is lying beneath our feet. It's permanently put in the stone, in the deposits, in the ice cores, and what have you. And the data does not lie. We just have to know how to interpret it.
Yeah. It is a library, isn't it?
It is a library.
Yeah.
Remarkable. Ray, thank you for sharing some of this. I think it's going to stimulate a lot of thought, get people hitting the Google a little bit, looking around, and of course we're going to be cross-linking a lot to many other posts that are up now and will be coming and continue to come on cyclesresearchinstitute.org. Look for that and find out more, and as we find out more, so will you. Thank you for listening with Ray Tomes, Cycles Research Institute.
You remember Afanasiev's book
and
his method of nanocycles for determining geological cycles. This is a graph I made which is useful to consolidate that large table. It shows how the period of the lunar orbit, it was 9.3 years at present, but it's been changing gradually over time. When we go back, we found the interaction effect of 9.3 was 31 years, and as we go back further, this becomes more and more. And I'm missing some of the lines here, but there are certain points at which the secondary cycles show up. There's actually a lot more detail in there.
Yes.
But it's just showing how over time the cycle's present, and if we've got two cycles of that period and that period, we can say that's at that historical period in the past.
Indeed.
Yeah. It's a graphical representation of the table.
Marvelous.